Hi, I'm Kevin, and today I'll be talking about a recent application of algebraic methods to algorithm design. This talk is based on joint work with Cornelius at Charles University, and it will be appearing at iCalp 2021. So I'm going to start the talk by introducing some notation and defining a general algebraic problem. Next, I'll show how a specific graph problem arises naturally as a special case of this problem. And after you've hopefully been convinced that the general problem is worth studying, I'll present our main results and state a few more applications. These will mainly be faster deterministic algorithms for certain combinatorial problems. In the remainder of the talk, I'll sketch our algorithms, and finally I'll conclude with some further questions. Throughout the talk, I denote by Q bracket X the space of n-variate polynomials with rational coefficients. Often we'll be interested in polynomials that are homogeneous of degree k, meaning they're a sum of monomials, all of which have the same total degree, k. I'll denote this space by adding the subscript k. For two polynomials f and g, we'll define angle f comma g to be the result of replacing the variables xi in f with the partial differential operator partial xi, and then applying that resulting operator to g. Okay. I'm going to use this notation a lot, so let me just make sure it's clear with a quick example. If f is equal to 2x1, x2 plus x3, and g equals x1, x2, x3, then just replacing these variables in f, we get this partial differential operator here. And at this point, you just differentiate g using the ordinary rules of differentiation. And you get 2x3 plus x1, x2. Now it's easy to see that if f and g are both homogeneous and of the same degree, then this inner product type thing just gives you a scalar. And you can think of angle fg as being like a weighted dot product of the coefficient vectors of f and g. And the weights will be given by some product of factorials. And it's also straightforward to see that this actually gives you an inner product in this case. So in this talk, we're interested in computing this inner product in the case when f is given to us as an arithmetic circuit, and g is the determinant of a matrix x whose entries are degree 1 polynomials. And this will turn out to capture many combinatorial problems as special cases. So to summarize, given some homogeneous degree k polynomial f as an arithmetic circuit, and a k by k matrix x whose entries are linear forms, we want to compute this inner product between f and the determinant of x. Let me now show you one application of this problem that's been studied extensively. So say you have a graph G on n vertices, and you want to decide if it contains a cycle of length k. Now here by a cycle, I mean a closed walk that doesn't revisit any vertices. So for example, in this graph here, this red thing is a cycle, according to my terminology. So to solve this, I'll start by associating to each vertex vi in G, the variable xi, and then we'll define this matrix AG, which will be an n by n matrix whose ijth entry is the variable xi if there's an edge from vi to vj, and this entry will be 0 if there is no such edge. we'll then define the polynomial CWGK as the trace of the kth power of this matrix. So it's not difficult to show that this trace of this power is equal to the sum over all the closed walks of length k and g of the product of the variables associated to the vertices along the walk. So this is sort of, you can think of this as a kind of closed walk generating polynomial for the graph. And in particular, a monomial xi1, xi2 through xik appears in CWGK with no variables repeated, that is, I1 through ik are distinct integers, if and only if the corresponding vertices form a simple cycle in the graph. Okay, and we'll call such a monomial square-free. So there's a square-free monomial in CWGK if and only if there's a simple cycle of length k in the graph. Now suppose we have some polynomial g that's a strictly positive linear combination of all of the square-free monomials of degree k, which there are n choose k of. Note. Now, recalling that this inner product essentially just takes the dot product of the two coefficient vectors, it's clear that this inner product will be positive if and only if there is a cycle in G of length k. Okay, so we'd like to compute this inner product. Now I'll describe one such G that has this property that turns out to be a very good choice, although why it's a good choice will not be clear yet. So we start by taking V to be a k-bion matrix whose ijth entry equals j to the I, and we take D to be this diagonal matrix of variables, and then we'll define X as VDV transpose. Then from the Cauchy-Bonnet formula, we can expand this out and see that indeed the determinant of X has this property that it's a positive linear combination of all the square-free monomials. Okay, so this matrix X has an additional property which will be useful to us. So, for example, if we look at what happens when n and k are both 3, you see that the matrix has a sort of structure where the northeast-southwest sloping diagonal entries are constant. Okay? So a matrix with this property is called a Hankel matrix. And indeed, it turns out that in general, the matrix X we've defined as in this way will always be a Hankel matrix. It's not too difficult to show that. So now I'm going to state our main results and show how they can be used in a cycle detection problem. So we have some matrix X of linear forms, and we have an arithmetic circuit C computing a polynomial f, and we'd like to compute this inner product between f and the determinant of X. So we show that under no assumptions on the matrix F or the polynomial f, we can compute this inner product with 2 to the omega k times the size of C, poly k, many arithmetic operations, where here omega denotes the exponent of matrix multiplication. Furthermore, if the circuit C has a property which is called being skew, I'll explain in a second, then we can improve this exponential factor from 2 to the omega k to 4 to the k. So this is the runtime that you would get if omega equals 2. And if, in addition, the matrix X is a Hankel matrix, then we can improve this exponential factor to phi to the 2k, where here phi is the golden ratio. So this exponential factor is roughly 2.62 to the k. So here, when I say a matrix is skew, it means the following. So for every multiplication gate in the circuit, one of the two operands is a variable. So the circuit never multiplies two polynomials together that both have degree greater than 1. And to repeat a matrix, X is Hankel if these northeast, southwest sloping diagonal entries are constant. And this matrix VDV transpose I defined before happens to have this property, I claim. So now let's return to the problem of detecting cycles. So it follows basically by definition that the closed walk generating polynomial can be computed by a polynomial-sized skew circuit. And from this, it follows immediately that we can detect a cycle of length k in phi to the 2k times poly n time. So here I'm using the result of the previous slide. And I guess I'm also using the fact that the only arithmetic operations we ever do involve small integers. But this will always be the case, essentially. Okay, and more generally, we can use the same idea to detect not just cycles, but any k-vertex subgraph that has bounded path width. And we'll get the same phi to the 2k poly n time runtime. And this matches the fastest known algorithm for this problem of detecting subgraphs of bounded path width, which is due to Fomin, Lokhshtanov, Panolin, and Sorab. And we use a different, shorter approach, although our algorithm does not work as well for general weighted graphs as theirs does. So now let me state a few more applications very briefly. So the details of these can be found in our paper. We give a phi to the 2k times poly n time deterministic algorithm for detecting k internal outbranchings in a graph, which improves on the previous fastest deterministic algorithm for this problem due to Brand. We also obtain a very simple 4 to the k poly n time deterministic algorithm for deciding if a subspace of k by k matrices contains an invertible matrix. And this improves on the previous fastest algorithm, which was given by Gurvitz. And I'll just mention that the problem of giving a polynomial time algorithm for this problem is a major open problem in complexity. Okay, and a third application is a faster algorithm for the k-matroid intersection problem, and this improves on a result of Fomin et al. So now let me give a quick sketch of how our algorithms work. So we'll start with some spanning set for the vector space that is spanned by all the partial derivatives of all orders of the polynomial determinant of x. So you take this polynomial determinant of x, you differentiate it in any way you can, and you look at the span of all the things you get by doing that. And we'll call this set L. So for instance, when you differentiate the determinant of x, obviously, this is true for any polynomial, you'll be left with some polynomial of degree at most k, and therefore you can just take L to be the set of all monomials of degree at most k, of which there are n plus k choose k. So one important observation is that actually when this polynomial is the determinant of a k by k matrix, you can take L just to be the set of determinants of all square submatrices of x. And there are 2D choose D such submatrices, which is around 4 to the k. So we can get away with a much smaller spanning set L. And this observation can be shown by expanding the determinant and using the product rule, and also Laplace expansion. So now what we'll do for our algorithm is we're going to compute the inner product inductively using the circuit C, starting from the input gates and working our way to the output gate. So suppose that at some gate I, the circuit C computes the polynomial, let's call it Fi. Then at gate I, what we want to compute is a linear combination of elements in L that is equal to the result of differentiating the determinant of x by Fi. And if we can do this, then note that at the output gate we will have computed the desired inner product. So at each gate we'll need to store a vector whose length is equal to the size of our spanning set if we do this. Okay, so now suppose we've managed to do this for the inputs to some addition gate, and let's say this addition gate adds the result of gates I and j. Then we wish to compute the inner product between Fi plus Fj and the determinant of x. Now, by bilinearity of this inner product, this just splits as the sum of these two polynomials, which we're assuming we've already computed at gates I and j. So all we have to do in this case is add the two vectors we computed at the previous gates, which can be done in time linear in the size of L. So addition gates are pretty easy to handle. The difficulty comes with multiplication gates. So recall that if C is skew, then any multiplication gate will compute the product between the output of some gate I, so some polynomial Fi, and some variable xj, let's say. So we'd like to compute this quantity here on the left. But since these differential operators just commute, this is the same as differentiating the result that we're assuming we've already computed at gate I. Okay, so basically the main problem is given a linear combination of elements in L, we need to be able to differentiate them with respect to any variable xj and output the result as a linear combination of elements in L. Okay, so we need to be able to differentiate efficiently with respect to the spanning set L. So in the current case, when L is the set of all minors of the matrix X, this is pretty easy to do just using basic properties of derivatives. Now the more involved case is when X is a Hankel matrix. So in this case, we show that there is actually a spanning set for the space of partial derivatives of the determinant of x of size less than phi to the 2k. And this spanning set was studied in a paper of Conca in commutative algebra, conveniently. And using an identity from this paper, we show that this differentiation step can again be performed efficiently. So these are all the main ideas needed for our algorithms in the case when the circuit C is skew. Now I'm going to conclude with two questions. So first, recall that for the correctness of the cycle detection algorithm, it was important that this polynomial, the determinant of x, was a positive linear combination of all square-free monomials. Okay, this was the first important property that this polynomial had. And then, for efficiency purposes, it was important that the space of partial derivatives of this polynomial was small. So one very natural and very interesting question is whether there's a choice of G that has this first property, but whose space of partial derivatives span an even smaller space. So finding such a polynomial could give insight into designing faster deterministic algorithms. Now finally, recall that the runtime of our subgraph detection algorithm for graphs of bounded path width matched the runtime of an algorithm for the same problem due to Fomin et al. So it seems like there should be a reason for this, but I don't know an explicit connection between them. So that would be something that's interesting to find out. Okay, thank you. And here are the references.